I would like to thank Saurabh and other organizers for inviting me to say a little bit about fundamental things about magnetism. So my talk is fundamental understanding of magnetic phenomena, DFT and beyond. That means I will bring you back to the ground state from the excited state, what Manish was talking about. And I just want to just acknowledge the main two persons. When I talk about magnetization dynamics, Raghuvi was my former PhD student, now a postdoc in Harvard National Lab. And this, unfortunately, I won't have time to talk about coupled electron-ion dynamics. And this is Raquel, is my present PhD student. We are working on how to go beyond Born-Oppenheimer molecular dynamics simulations. Today I will talk about magnetism only. And when I talk about magnetism, the first thing comes to my mind is all the devices that you are holding in your hand. Now somebody maybe is looking at the mobile phone, checking Facebook or Twitter or something like that, and somebody is looking to the computer. So if we try to understand what's going on inside these devices and try to see the fundamental phenomena, then you will find extraordinary things. And I'm going to tell you a little bit about it. So that means we're dealing with enormous amount of information nowadays, and these information, we want to process it very fast. We want a huge amount of information to be stored, and we want to bring them back, we want to process them, then store it somewhere. So it's a big business, you know. So what I want to say is that we are in the information technology, but we are towards innovative information technology, and the innovation is a perpetual progress, and it's a very fast progress. If you look at, I don't know whether you can read it, but this is the number of transistors on the y-axis on a chip, integrated circuit chip, and this is on the x-axis, this is the number of years, so how the number of transistors they develop. And you see now in the current era, we are using around 20 billion transistors in a chip. So this is an enormous thing, and this came from, there was a prediction from the co-founder of Intel, Gordon Moore. He gave this famous Moore's law. He said that the transistors will double in number every 2 years, approximately 18 months in practice. So sometimes we get even steeper increase than that. So not only the number of number of transistors in the chip, but also we want to increase our storage density. We want to have smaller devices, and we want to store more and more data in smaller and smaller devices. That means the storage density must be increased enormously. And this is a picture where you see the areal density gigabits per square inch, once again versus year, and now we see that we have, you know, if you go to a computer shop nowadays, then you can buy easily a terabyte hard disk, 2 terabytes, 4 terabytes easily. So this is an enormous increase in the storage density. This is needed because otherwise Facebook and all these big companies, they don't have data to store somewhere. Typically, the perpendicular magnetic recording is the technology that is used, but what is Seagate is actually bringing in quite recently, I mean, or in very recent future, they will bring in the heat-assisted magnetic recording, in short from HAMR technology, for the hard disks. So I had a privilege to work with Seagate, and they told me many stories about it. So anyway, let's go back a little bit of time. So this is only for the students who maybe are much younger and they didn't follow this progress too much. So the whole era of spintronics, that means playing with the spins of electrons. I mean, that started around in the early 90s or late 80s, when these two gentlemen, Albert Fett and Peter Greenberg, they independently discovered a fantastic phenomenon called giant magnetoresistance. So it basically tells you that if you have two ferromagnets aligned parallel or aligned anti-parallel, depending on the mutual orientations of magnetization, the current flowing can be, the amount of current flowing or the number of electrons you can let them pass through it from one side to the other, that changes drastically. So that means by the orientation, by changing the orientation of the magnetization direction, you can influence the number of electrons that passing from one side to the other. And this effect was a big effect. That's why it is called a giant magnetoresistance. Why it is so useful? Because after their discovery, IBM became interested, and they started to put this principle into devices. And this is the device that we have. This giant magnetoresistance principle is used in the reading heads of our hard disks. Our hard disks have a reader part and a writer part. So the reading part works on the principle of giant magnetoresistance, where this head runs over the stored media, and it basically finds out in Boolean whether there is a 0 or 1 based on this principle. And this was so extraordinary that they were awarded Nobel Prize in 2007. So not only that, but there are other extraordinary effects that those have been proposed. For example, the spin field effect transistor. So if you want to replace your charge-based devices by spin-based devices, utilizing the spins of electrons, because we know that the electrons have both charge and spin. It's a quantum mechanical object. So there was a proposition that whether the normal charge FETs can be replaced by spin FETs, utilizing a device like this, that from a ferromagnet you inject the spins and it goes through the base like that, and it goes to the collector region like that. But in between here, with the help of a gate voltage and via Rashba effect, you can actually control the direction of the electron spins, and then you can control that how many electrons can go from this side to that side. You can control that number with the help of the gate voltage. But unfortunately, this has not been realized in practice because of many practical problems. One of the practical problems is actually to find out proper materials to use in these devices. Because if you go to an experimentalist, if you show a picture like that, that person will laugh at you and say that, oh, this is just a cartoon picture, it means nothing to me. Because if I want to grow a sample on top of this sample, you have to think about so many parameters. So materials characterization, choice of materials, these are very important issues for material scientists like us. And that I'm going to talk a little bit about it. So the other thing is, of course, I have discussed a little bit, you need a ferromagnetic electrode with high spin polarization. You can think of a metal, ferromagnetic metal like iron, where you want to inject some spins to gallium arsenide, standard semiconductor, but immediately you see that there is a problem because this is a metal, this is a semiconductor. They have a huge resistance mismatch, and it will not work so efficiently. So then people thought about another class of materials, which is called the dilute magnetic semiconductor. Some of you have worked rigorously with it. This is the all semiconductor spintronics. That means we have everywhere a semiconductor. The ferromagnetic part, we have to have a semiconductor doped with some magnetic elements to make it a ferromagnetic semiconductor working ideally at room temperature or beyond, above that. So this started in the early 2000s. This research started, and thousands and thousands of papers have come out, but there is no single ferromagnetic semiconductor to date with a room temperature ferromagnetism. So the result is rather, research maybe sometimes goes like this, that and then even with a lot of trials, you don't achieve your goal. But that's okay. In the process, we learned a lot of things. So the question is, so if this is the scenario, so being a material scientist, a computational material scientist, what can we do? What can we contribute? So, of course, fundamental understanding of magnetic phenomena, what is happening in a microscopic scale, in the scale of electrons and atoms, what is happening, we can actually look using our DFT-based simulation, sometimes going beyond DFT. And some of the things that we can actually calculate, and some of the things I'm going to discuss here. For example, saturation magnetization. So this we can calculate, and this can be readily compared with experiment. So until and unless you compare with an experimental value, the experimentalist will not trust you at all. I'm going to show you that this works. Saturation magnetization, magnetic anisotropy, which is basically related to spin orbit coupling. Magnetic anisotropy is another very important thing because that can tell you whether material has a perpendicular magnetic easy axis or an in-plane magnetic easy axis, and that is extremely important for not only for the experiments, also for the technology, for the devices. Of course, magnetic exchange interactions, these are very important things because that gives us the idea that whether the local magnetic moments you have in your system, whether they're going to interact with each other at a finite temperature, at a temperature that we want them to interact, let's say at room temperature, whether that will happen or not. Finite temperature magnetism. So far, all the DFT calculations that we have been shown, or methodologies have been shown, they are done at 0 Kelvin. So how do we tackle a finite temperature magnetism? We need to worry about that. Correlated electron behavior, some aspects were discussed by Professor Maiti yesterday. I will try to say a little bit about it. Spectroscopy is a very important thing where you can have a direct comparison between theory and experiment. Several types of spectroscopy experiments: valence band photoelectron spectroscopy, X-ray absorption spectroscopy, X-ray magnetic circular dichroism. These are these are element-specific methods, very powerful synchrotron-based techniques. Magneto-optics, spin orbit related phenomena, and lastly, ultra-fast magnetization dynamics. So this is what is happening nowadays, that people are trying to figure out how you can switch magnetization in a faster time scale. I will try to cover that if I have time, I don't know. Let's start from a basic. Let me remind you about some of the basic things. So we have gone through this equation again and again. This is the Kohn-Sham formulation of density functional theory. You know all these things. You have the exchange correlation functional, you have the Hartree torque, external potential, etc. You have the density here. Density is written in terms of the single particle Kohn-Sham orbital. The important thing, if you want to do a spin polarized system, you need to extend this idea. And this generalization to spin density functional theory was done by Barth and Hedin. And the same Hedin who did the GW theory, Barth and Hedin, generalization to spin density functional theory. So what was done is rather straightforward actually. So the density, which is a scalar variable here, if you want to consider to a spin density functional theory, a general theory requires a 2x2 spin density matrix. So this is a 2x2 spin density matrix in terms of these single particle orbitals, but now they have these indices alpha and beta, meaning the up or down spins. And you can write it in a little bit different way, where you have the normal charge density here that you get from the normal non-spin polarized density functional theory, and the magnetization density having a scalar product with the Pauli spin matrices. This is a formulation that you can find in many textbooks and things like that. So if you expand it in a matrix form, it basically looks like this. There's a 2x2 matrix. So if you look into this one and that one, these are basically the Z component of the magnetic moment. And the off-diagonal components here and here, they have the X and Y components of magnetic moment, complex quantities. So this is now for spin density functional theory. It's a 2x2 matrix, and it has off-diagonal component. We have to remember that. So not only spin density matrix, but the potential matrices can also be written in a similar fashion as a dot product of the Pauli spin matrix with the magnetic field, and this is the exchange correlation part that is also rewritten for a general spin density functional theory. So if you take into account all these things, you can actually look into very complex magnetic structures. Now, so this is the general form of spin density functional theory that can give access to non-collinear magnetism, spin orbit related phenomena, all sorts of things where you have off-diagonal components in your spin density matrix. So this is a typical picture that you can generate. This is the magnetic ground state of hexagonal chromium monolayer. Now this is a full potential calculation where you see all these, most probably you cannot see from a distance, but I can see that this is a magnetization density which is defined at they have a very nice agreement with each other. So it's I would say it's a very good agreement between the spin moments, between theory and experiment. So that gives us a lot of confidence that we can use the spin density functional theory. I can show you more. These are now for more complex cases. These are random binary alloys, and you need certain techniques to treat these random alloys. Let's not go into that. For example, here is a technique, coherent potential approximation was used. I guess you can see that, let's say this is the iron cobalt alloy. Average magnetic moment is plotted here as a function of effective alloy number. That is basically you alloy between iron and cobalt. You change the concentration and you go from this side to that side. Let's look into the iron cobalt part only. The bold line is the theoretical calculation for BCC phase, and these circles are the experiments. So this is a fantastic agreement between theory and experiment for iron cobalt LNC. They really follow the theory curve. The experiments and theory are right on top of each other. Sometimes we see some deviations. This is the FCC phase of iron cobalt. We see some, these are the experimental numbers, this is theory. We see some deviations, but we can, there are some discussions corresponding to that. FCC phase is always a very interesting phase because it can generate lots of magnetic frustration. Anyway, so so far so good. So these are ground state static properties like magnetic moments. We can reproduce the experimental results pretty well. We are very happy with that. But this is not enough. What we need to have a theory for finite temperature magnetism. Because at high temperatures, at T not equal to 0 temperatures, usually all the experimental results, they are more relevant there. How should we actually, what kind of theory we should have? So I'm going to show you one way of doing this, but there are other ways of doing. I'm not going to talk about that. So one way of treating finite temperature magnetism is to do a DFT calculation, take the parameters from the DFT calculations and do Monte Carlo simulations with these parameters. What you essentially do, you map your DFT to an effective spin model, a spin Hamiltonian basically, which can be a classical Heisenberg Hamiltonian. So this is a classical Heisenberg Hamiltonian which has this quantity Jij we called. It's an exchange parameter, it's called, interatomic exchange parameter between site I and site J. There are two magnetic moments, and these magnetic moments are coupled via these interatomic exchange parameters, and these are some unit vectors, spin unit vectors for I and J at site. So the question is that this quantity is of primary importance, because if that is zero, in this convention, if this is zero, it means that there is a ferromagnetic interaction between these two atomic moments. If this is less than zero, this is it shows us this is an antiferromagnetic interaction. So if we can calculate these GIJs with this from the sign and the strength of the interaction, we can say a lot of things. Now, there are different ways of calculating GIJs. One of the standard ways to use a Green's function approach. Manish was talking about Green's function approach. So this is based on, this calculation of GIJ is based on Green's function multiple scattering theory approach. let's not go into detail, but this you can see an integral, energy integral here, and in its bracket you see imaginary part of trace of different quantities. These are basically related to scattering properties. So electrons scatter from one side to the other side, and these are related to spin-dependent scattering properties. That gives you the idea of your exchange interaction between two atomic sites. Now, once you have these GIJs, typically these are calculated as a function of distance, because you know in a solid, two atomic sites can be placed at different distances, and as a function of distance, you can calculate these interatomic exchange interactions. So once you have that, then in the next step, what you do a Monte Carlo simulation. So you take a Heisenberg model once again, and for this Monte Carlo simulation, you have these GIJs now calculated from density functional theory, material specific parameters. You don't have to do anything else. Then you do Monte Carlo simulation. Some of you have already done this with standard Metropolis algorithm, and then you look into certain thermodynamic properties. Basically, you look into the phase transition, other thermodynamic properties, etc., etc. So one typical way of looking into the critical temperature, the temperature at which a system might go from a ferromagnetic phase to a paramagnetic phase, and that is by so-called calculating the fourth order cumulate crossing method. This is a standard method described in statistical mechanics. Also from the magnetization versus temperature or susceptibility or specific heat, if you plot versus temperature, you can find out where the magnetic transition is happening at which temperature. So first let me show you something for a very simple elemental ferromagnet, which is BCC iron. These are the interatomic exchange parameters calculated as a function of distance between a pair of moments. Three things have been shown here. One is from local spin density approximation, one is adding a U with that, and one is with dynamical mean field theory. So you can see that more or less they follow a similar trend, but there are certain differences because of different approximations that we use. Sometimes with static mean field or a dynamical mean field, the results are different, and there are lots of important discussions behind this, but let's not go into detail. We see that the first level interaction is very high, and then it goes down, and it goes down like this. Now, for a metallic ferromagnet like BCC iron, we know that the RKKY interaction plays an important role. So this is a very long-range interaction. That's why these calculations have to be done very carefully to find out for long distances whether these are really ferromagnetic or anti-ferromagnetic. So once again, the GIG is positive, means this is the ferromagnetic regime and this is the anti-ferromagnetic regime. So now once you have these exchange parameters calculated from DFT, then you can proceed towards Monte Carlo simulations, and you can get a curve like curves like this. So this is the magnetization versus temperature in Kelvin. You see how the magnetization behaves as a function of temperature. This is the textbook picture. You have seen all these Brillouin curves, Brillouin functions like that. So in our simulations, it looks like this, and there are discussions about the finite size scaling and all those things. Detailed discussions. Let's not go into detail, but you see that if you increase your system size, it becomes more and more exact. You can actually find the critical temperature more and more exactly. But the other thing I was talking about is actually looking into the cumulant crossing method, fourth order cumulant crossing method, as a function of temperature. So these are actually calculated here, three different curves for three different system sizes, and when they cross each other, that is the point where the critical temperature should be. Also, you can look into the susceptibility. It has a peak at the phase transition. Specific heat, it has a peak at the phase transition. So by several different means, you can find out the critical temperature for the system. So if you look into the experimental value for the critical temperature, that's the cool temperature, is 1043 Kelvin for BCC iron, and here from these simulations one can find it is around 900 Kelvin. So this is not too bad, this is pretty okay, but these numbers depend on crucially on the details of your simulations. For example, what is the exchange correlation functional you are using, whether you are using LSDA or something beyond LSDA, taking into account electron correlations or not. But there is a huge effort that goes on in this field, and this has become quite a standard way of looking into finite temperature magnetism. People do it quite regularly. Having said about electron correlation, there were discussions yesterday from Professor Maiti's talk that what is the role of a strong electron correlation, because that is something which is very important for narrow band systems. We all know that for d electrons, f electrons, they are very different from sp electrons. Sp electrons are very delocalized, d and f electrons are localized in nature. F is much more localized than the d electrons. So in order to describe the electronic structure of these d orbital based systems or f orbital based systems, your standard approximations of exchange correlation functionals like LSD or GGA may not be enough. You have to think a bit more about it. So one of the typical examples is actually transition metal oxides. For example, nickel oxide, manganese oxide, blah blah, there are many different oxides. So you can classify them as Mott-Hubbard insulators or charge transfer insulators depending on what are the relative positions of the d and the p electron states there. If you look into this side, this is a schematic diagram of the density of states. So this is independent electrons, or sometimes people call it non-interacting picture, because this comes from LD or GGA. You see that this is the D band, and the Fermi level is passing through the D band, telling us that this is metal. But in practice, this is not a metal, this is an insulator or a semiconductor. So what happens is that when we do the approximation of LD or GGA, the exchange correlation function is very much approximated to a uniform electron gas, homogeneous electron gas, where this homogeneous electron gas cannot take into account the localized nature of the electrons. And there this theory fails, and it fails to give us the correct electronic structure of the insulating character of the system. It gives us a metallic structure, which is wrong. So a poor man's view would be to actually add an extra Coulomb interaction with it in the form of this U, and what you do here, you split this band, metallic band, into two parts. You split by an energy value U, Coulomb, which is the value of the Coulomb repulsion, and what you have here, you have this sub-band which is filled, and you have this sub-band which is empty. So these are called the lower Hubbard band, and this is the upper Hubbard band, according to the John Hubbard's formalism, which is separated by a Coulomb repulsion unit. This is actually the correct picture. Here the gap opening is not coming from anything else, but it's coming from the strong electron correlation, which is absent in our normal standard approximations. So let's see how it works a little bit. I think many of you are working on this DFT plus U techniques. The idea came from John Hubbard. It's basically a Hubbard Hamiltonian where you have basically two terms. One is a kinetic energy term or a hopping term. If you look into this picture on the right side, this electron is actually hopping from one side to the other with a kinetic energy term T, hopping term, and which is negative here. But you have a repulsive term here, which is given by the Coulomb repulsion. And if you look carefully, you see that this is an on-site Coulomb repulsion. So that means when an electron comes to a site and finds another electron there, with an opposite spin, because Pauli exclusion principle has to be maintained, then these two electrons face a very strong Coulomb repulsion, and that is given by this U here. So you have basically a kinetic energy term and a U term, and the kinetic energy term dictates the bandwidth. You can show it very easily. So one term gives you the bandwidth of the system, one term gives you the Coulomb repulsion. So a direct comparison or competition between these two will give you the regime of correlation, which I will show you later on. But anyway, this is the basic starting point of the LDA plus U or DFT plus U formalism. And if you write your energy functional, you can say that this is by LDA energy. I want to correct this LDA energy by adding a strong Coulomb interaction into it. But now I know that I'm doing it a little bit wrong here, because already some exchange correlation is inbuilt in my DFT, so I have to take it out. And this is the so-called double counting correction. So the third term, you have so this is the Coulomb term, and this is the double counting correction that you. So you add a Coulomb term and you take out the double counting correction from there. And if you calculate the orbital energy, which is basically the derivative of the energy, total energy with respect to the orbital occupation, you will see that it looks like this. It directly comes from here. Now if you put NP, this occupation, is equal to 1, then you see that the orbital energy comes out as epsilon LDA minus U over 2. And if you put it 0, here in this expression, it comes out epsilon LDA plus U over 2. That means whatever you have, the schematic picture that I showed you at the beginning, the metallic band that you had, with the inclusion of the Coulomb repulsion, you have the lower Hubbard band completely filled and the upper Hubbard band completely empty. So you basically take them apart with U by 2 each at each side. So this is a schematic picture of that. And of course, a generalized LDA plus U functional is written similar to that, but in a little bit more rigorous way. And you can see that it has 3 parts once again: the LSD energy, the Hubbard U term, and the double counting term. Now the LSD energy, we know that when you talk about LSD, it depends on the electron density. It does not have an orbital character there. But this term and that term, these two terms, they have the orbital occupation. So this is, one can call it a kind of mixed approach. You have the density as well as the orbital occupation. Now one has to be. I just want to say that these corrections that you do, these corrections are done in only the correlated subspace, not for all orbitals, but for the correlated orbitals only. So it gives us a little bit of problem, because we don't change explicitly the ASP states in this. We only do the corrections in the d orbital subspace or f orbital subspace, and due to hybridizations, the other states might move a little bit, but we are not doing corrections for all the states, which is different from hybrid functionals, where we correct all the states, or even GW, where you take into account all the states. Here it is done in a subspace, correlated subspace only. Let's look into the results if you do a LDA plus U calculation. So this is gadolinium, ferromagnetic, 293 Kelvin, cool temperature, density of states versus the experimental spectra. You see that this is the XPS, that means it gives you the occupied part of density of states, and this is BIS spectra, which gives you the unoccupied part. And you see that basically if you do the correction on the F states, the F states more or less, they come to the correct position. So this was one of the earlier history of our earlier success. If you look into iron oxide, which is a transition metal oxide, if you do LDA calculation, a DFT calculation, you get a metallic solution. You see that this is the Fermi level, the bands are crossing the Fermi level. If you do DFT plus U, correction on the iron d orbitals, you open up the states, you see that there is there is a gap opening up which gives you the correct solution. So in some of the cases, we see that DFT plus U actually works pretty okay. Some comparison of magnetic moments here on the right hand side, or the energy gaps. One can say that there is reasonable agreement between experiment and theory, like this. Local spin density approximation is very bad in this respect. The energy gap as well as the magnetic moment is not so good in many cases, whereas the plus U and experimental results, they actually match pretty okay. I'm not claiming that this is the method one should use, because I guess you have been talking about how to choose U and all these things. There are certain methods to calculate U, and one has to use them with proper care. So this is the main field picture, but this is a static main field picture, the DFT plus U technique. But we should think of going beyond this picture and do something better. So I was talking about regimes of correlation. So one can actually look into different material systems, and you can divide the systems into different types of materials. For example, on the left hand side, I have a weakly correlated metal, normal metal. On the right hand side, I have a strong electron correlation present in Mott insulators like these oxides, where you see the lower Hubbard band and upper Hubbard band that opens up a big gap, things like that. So on the left hand side, LDA is good enough, weakly correlated metal. On the right hand side, LDA plus U is good because the electron correlation is very strong. The problem is that when something is in the middle, that gives us a lot of problem, which is a strongly correlated metal. So you have a strong correlations, but also a metal. In this case, what happens is that you have the lower Hubbard band, upper Hubbard band, but also you have a quasi-particle peak that is coming in between, close to the Fermi level. This you cannot get with LDA plus U thing. So you have to go beyond your static main field theory to capture this effect, and that brings to the question of the development of dynamical main field theory, where this is no longer a static theory, but it's a dynamic theory, where the self-energy is actually, you have heard about self-energy in the previous talk. Self-energy is actually dependent on the frequency. So basically, what is the few words, the principle? The principle is that you have a lattice model where you have all sides which have a Coulomb repulsion associated with it, and there is an electron is trying to hop from one side to the other. So this is an infinite lattice. The idea of dynamical main field theory is to map this infinite lattice to an effective impurity model, where you have one impurity embedded in a surrounding which we call a path. So the electron is getting constantly exchanged between this impurity site and the path state like this. And the self-energy actually describes these path states. It's a very simple words actually. So a lattice model mapped into an impurity model, and we have the self-energy, which has an omega dependence that we need to calculate. And that is one of the ways to actually look into this, that you for the impurity, you take the Anderson impurity Hamiltonian for solving this impurity problem. It looks complicated here, but basically the first term is the on-site term of this impurity here, the correlated levels are. And then the next term is the Hubbard interaction, the U term here, and then you have the hybridization between this impurity and the path state. That means it basically tells us the exchange, constant fluctuating exchange between this impurity and the path. And this is the path term, basically the kinetic energy in the path electron system. So if you follow these procedures, then you can generate some very nice results. You have some data of photoemission and X-ray absorption. Photoemission means you are probing the occupied part, and X-ray absorption, that means you are probing the unoccupied part. And different oxide systems, strontium vanadate, calcium vanadate with LDA plus DMFT, and with some experiments, you see the continuous curves are actually theory results, and these are the experimental results. You see these lower Hubbard band and upper Hubbard band, they're coming in very nicely, and you have the quasi-particle peak at the Fermi level. All these fantastic features, they come out if you do a dynamical infinity. Now, like we are discussing about the computational cost of GW calculations, but this is also computationally very heavy, because there are different ways of solving the impurity problem. Depending on what you use, your computational cost can actually go up. But slowly, this has become, I mean, I think nowadays people are using it I think people are normally using it, I mean, nowadays. If there is a reason, you can use actually the LDA plus DMFT. So I just want to show one of our own recent results is that this is the multiferroic bismuth ferrite, very famous multiferroic system where two orders coexist. One is the magnetic order, which is an antiferromagnetic order, and one is the ferroic order, ferroelectric order. Both of them are coexistent in this system. Very well studied system. Crystal structure looks like this. This is what we show here, is the comparison between the experimental spectra and different spectra generated by different theoretical methods. So these black ones are the experimental Hack space spectra. Professor Maiti was talking about. This is a high energy photoemission experiment. So you really bombard with high photon energy, something like 6 keV, 8 keV. So this is a very reliable result, it means. So you see the LSDA plus U, that result is the red curve here. It basically, there is a peak here which does not exist in experiment. So previously people thought that LSDA plus U is absolutely good for bismuth ferrite. People have done that. Quite a lot of papers are there. But when we did that, it was a surprise to us that this is really not so good actually. If you do DMFT, then you see that the peaks, more or less, they match very well with the experiments. So this is one example where the dynamical mean field theory is winning over the static version, which is LDA plus U. So if you're interested, you can have a look into the paper. Now, in the last few minutes, I'm going to talk about another aspect of magnetism. I have been talking about static aspects of magnetism, like static properties. But now let's go to a more dynamical properties and see that whether we can actually have some time-resolved experiments, whether we can actually do something from our theory for time-resolved experiments. The idea comes like this. So we want to process information in a very fast and efficient way, right? That means, in other words, we have a magnetization direction, let's say up. We want to flip that, or want to have a magnetization reversal of that, downward direction in a fast and efficient way. So far, people use magnetic fields to switch the magnetization, like up to down, down to up, something like that. But that has limitations in the time scale. So typically, when you use a magnetic field, you operate in this time scale that is given here, nanosecond to a few hundreds of picosecond time scale. The magnetization switching happens in that time scale. But what we want to switch them even much, much faster. So what should we do? There is another reason for that we can actually look into the different interactions, like spin orbit interactions or exchange interaction. They operate in a much, much faster time scale, in the femtosecond time scale. So that means we need something that can actually give us access to switch the magnetization from up to down, down to up in a femtosecond or tens of femtosecond time scale, and magnetic field cannot do it. So the idea is that, is there an alternative to the magnetic field? And people said yes, because lasers operate in this time scale. So the question is, can femtosecond laser pulse create a faster magnetization reversal? Instead of a magnetic field, You shine with a laser, and that laser will actually switch the magnetization. So this is a very recent development in the field of magnetism. I would say recent because the first demonstration of this successful demonstration came in 1996 by this group in PRL. They showed that you can really change the magnetization or demagnetize FCC nickel. This is the FCC nickel film. FCC nickel with a 60 femtosecond laser pulse in a time scale you can see is of the order of picoseconds. This is the so-called pump probe experiment. If you do that and if you measure the longitudinal magnet-optical curve effects, so you can actually look into the remnants here. The demagnetization happens in a few picosecond time scale. That means very fast with a laser pulse. Now the moment, so this was a remarkable experiment, first time demonstration. And you can understand that if you shine laser on a material, many complex things will happen. Because first of all, it will create a highly non-equilibrium situation. Because the system is getting a large amount of energy. And we know that in our system, what we have electrons, we have phonons, we have magnons, all these things. That means we have basically three subsystems, electrons, lattice, and spins. They are excited and they are constantly exchanging energy and angular momentum among themselves. And in this very first few femtosecond time scale, tens of femtosecond time scale, when the system has not been equilibrated or thermalized, lots of very complicated scattering processes occur. So we need to understand those things. If we can do it in a microscopic way, then it will be the best. But when people started this thing, nobody knew how to do it, so they took help of a phenomenological theory. This is a phenomenological theory in terms of a 3-temperature model. That means you define 3 temperatures for 3 subsystems. One is an electron temperature TE, one is a lattice temperature TL, and another one is a spin temperature TS. And you write down 3 coupled differential equations where these things are connected to each other. And then you solve them, and then you find out that with time, delta T, that is the pump probe delay time, how the temperature actually behaves. So this is the experimental profile actually. This is actually measured in experiment. And if you follow the 3-temperature model, if you simulate it, you get a profile also like this, which is very nice. But that is the profile for the electron temperature. Now you see that what happens is that when you shine laser on the system, electronic system gets excited first. It becomes heated, it gets excited, and then it starts changing its energy with other subsystems. So you see that when it goes down, when the electron temperature goes down at the same time, the lattice temperature and the spin temperature, they go on. And finally, at a long time scale, they all merge together and the system is thermalized. So this is one of the this is the phenomenological model which is actually used, and later on other people also used, including us. Now you can do many important advanced experiments. For example, based on synchrotron-based radiations, X-ray magnetic circular dichroism, you can probe the signals as a function of time now. Now many people, many groups have done that quite recently.
If you shoot very high energy ions also, they more or less interact in the same way. And there the temperature development given explained by 2 components. Spin component is not necessary.
Yes. That can happen, but now this is a light matter interaction, so that the electromagnetic wave actually comes, that has its own characteristics, that interacts in a little bit different way.
Here the spin temperature part is also important.
Yeah, it is very important actually, extremely important. So now if you look at the X-ray magnetic circular dichroism, So you see that actually this signal, it goes like this as a function of time. So this is like this. The interesting thing of doing an eccentricity measurement is that you can get access of the spin moment and orbital moment. I don't know about any other experimental technique by which you can get the orbital moment. That's right? So this is a very powerful measurement, element specific. That means if you have several components in your system, you can selectively choose your photon energy to probe each of the elements separately. And you get the information which is completely element specific. That means spin and orbital moments of iron, cobalt, nickel, separately. Extremely powerful technique. But you have to go to synchrotron center to do this experiment. Now this is even more advanced because this is measured as a function of time. Usually it is measured in a static way, but this is measured as a function of time. And some clever people, they can actually find out the components of the spin and orbital angular momentum like this. And like this is the spin angular momentum component, how it decays with time. This is the orbital angular momentum component, how it decays with time. And from there, you can estimate that there is a strong coupling between spin angular momentum and orbital angular momentum. Spin orbit coupling. So that means it tells us that in this highly non-equilibrium situation, spin orbit coupling is extremely important. Based on, so this is direct experimental evidence of that. Now there have been different theoretical models of demagnetization. So some of the notable models are Elliott-EFET mechanism, where phonon-assisted spin flips scattering is actually involved there, or electron-phonon mediated spin flip scattering. Or from our group, we have a theory called super diffusive spin transport, which is based on Boltzmann equations. So people are trying very hard to find out a microscopic model, but which we are still far from there. Because as I said, that there are lots of scattering mechanisms, and in order to find out a microscopic picture of these scattering mechanisms, it's very difficult. We are still very far from there. As my time is running out, I won't be able to show you any result today, but what I want to show you that what we do is that how we utilize density functional theory in this whole business is that we take this phenomenological model, 3 temperature model, or sometimes it is modified to 2 temperature model. So that means we solve the coupled differential equations, and then we get this every time we get the electron temperature, let's say, and the spin temperature here. For this electron temperature is passed to density functional theory. That means we calculate the static properties as a function of electron temperature. So now this is, I'm talking about temperature dependent things one can do in DFT with a Fermi-Dirac distribution function. You can do it. Anybody of you can do it. So magnetic moment as a function of electron temperature, and the exchange parameters as a function of electron temperature. Also, the spin temperature is actually passed to the atomistic spin dynamics simulations, where the magnetization is calculated as a function of time and also as a function of spin temperature. So this part we can understand a little bit, but what is this part? Atomistic spin dynamics. So I want to show you that, and then most probably I have to finish that. So this is the development in our group. This is atomistic spin dynamics. That means how the atomic moments evolve with time. You understand that. So let's say this is an atomic moment here, this arrow. You know that if there is a field, it will just precess around the field like this. That is the first term here, which is the precession term, that the magnetic moment rotates like this. But the next term is called a damping term that brings that rotating moment brings it and makes it aligned to the effective field here eventually. So it is not, if you only have the precession term, it will not decay, it will not be aligned with the effective field, but you need this damping term in order to have this moment slowly come and they become aligned with the effective field. This is all about the so-called Landau-Lifshitz-Gilbert equation. This part is, this alpha is called the Gilbert damping parameter, which plays a very important role that how slow or how fast this is going to happen. So now, there are several terms here. So this is a stochastic magnetic field that you can actually put it in with a Gaussian white noise. And this amplitude of the stochastic field is actually related to the spin temperature. So when you pass the spin temperature into it, that comes directly here, that gives you the amplitude of the stochastic field, and then it's a stochastic, so it basically involves the random number things or things like that. And that gives you this field, and BI, capital BI, is actually the effective field, which is the derivative of the Hamiltonian, spin Hamiltonian with respect to the local magnetic moment. Now, this thing is usually done in the micromagnetic simulations where the similar thing is done there, but they do not consider atomistic approach. They do not have the atoms or the atomic moments. They have a chunk of macro moment, and they work with that. But the difference with that, we have the atomistic approach. That means every atomic moment is considered here. So now this Hamiltonian we have. Now the final thing is the how do you define your Hamiltonian? Your Hamiltonian can be very large with all sorts of different terms. Here mostly we use the classical Heisenberg Hamiltonian for the exchange parameters, and the magnetic moment are, both the exchange parameters and magnetic moments are calculated from ab initio DFT techniques, and we put them there, and then you generate the effective field and let the atomic moments evolve within this effective field. So there is a code that has been developed that does that atomistic spin dynamics. So I want to stop here. If anybody is interested in any application of all of these complicated things, I'm ready to discuss with people. But basically, I guess I could convince you with that you can do a lot of important things, considering the experiments and also technological innovations from your fundamental DFT simulations and beyond, going beyond DFT sometimes, utilizing different types of methods that I showed you. And I want to finish here and thank you for your attention.
So we'll take just one question.